So let us talk about the projectile motion and the relative velocity. So let's start with the projectile motion first. So hearing this, what comes in the mind first, that a motion which only occurs due to the presence of the gravity. So the presence of the gravity is pivotal right here. If an object is being thrown at v0 velocity along the angle with the horizontal, it will create a sort of trajectory, like a curved trajectory, and this motion which is formed is called projectile motion. Let us go a little bit further. An object is thrown with a velocity v0 and along a theta naught angle with the horizontal, it created a trajectory, a curved trajectory. Now we have to observe, to point out our observations at every point. By that we can pretty much understand the insides and outsides of this motion. So if we want to learn this very distinctively, so I have to do that. At every point I have to observe the what is happening, what data we can collect from here. So by that we can have a better understanding about this motion. At every point you see that at initial the x is equated to 0, the y is equated to 0. Okay, the velocity is not 0, it's something meter per second, so it could be anything. Okay, it's traveling following the trajectory. So let us assume that it traveled this much. So at this point, then this point, at this point, in this point, at this point, and the final point. Okay, so here assume that the v0 was 30 meter per second. If we assume, so here let us assume, let it be 20 meter per second. Let us assume that it's 10 meter per second, it's 0, it's 10 meter per second again, but negative. This is negative 20 meter per second, this, and this is negative 30 meter per second. Right before touching, it's not touching the ground, right before touching the ground. So what is happening actually? If you see that the velocity right over here is gradually decreasing, the velocity is decreasing, but the speed is increasing at a certain point of time, and then it's decreasing. When it's increasing and when it's decreasing, that's our concern. So the speed when it's increasing is when it's getting downwards. but the speed when it's decreasing, when it's getting upwards, if you see that it's being 30 meter per second, if I consider it to be a speed 30 meter per second, 20 meter per second, 10 meter per second, 0 meter per second, then it turned out to be 0 meter per second, then the speed is not a vector quantity, so we will not consider this minus over here, so it will be written like 0 meter per second, 10 meter per second, 20 meter per second. Again, it's similar to these datas, but at the other side, and the acceleration is downwards. So you see that the speed is increasing at a certain point of time, and the speed is decreasing at a certain point of time. Why it is decreasing and suddenly it increases? What makes the speed increases? What makes the speed increase? The thing made the speed increase was the maximum point. The maximum point right over here. This is the maximum point, and this made the speed increased. So how it made the speed increase? How it made the speed increasing was the Vy was equated to 0. That's how the speed increased. At a certain point of time, the velocity turned out to be 0. Then the object moved in the favor, along the favor of gravity. In the first phase, it was going against the gravity. Then at a certain point of time, when the velocity turned out to be 0, it traveled in favor of gravity. So that's a very, very, very vital observation. So Vy is equal 0. It is the main reason why the speed increased at the second phase. Okay. Now, if I draw the same picture and the same curve, now our target is to get the informations at the three major points. At three major points, we have to get the information. This is initial. This is the first point. This is the maximum point. And this is the final point. So at the initial, what we get is the x is equal 0, the y is equals 0, the v naught exists. It's not equal 0. Then it rose up to and it reached the maximum point, and at the maximum point, what informations we got was, we got the Vy turned out to be 0, we got the maximum height. And we got our T1, which is time of rising. At the final point, what we got was the y becomes 0, we get the T2 and the time flight. The T2 is the time of falling, and this is time flight. And then 3, the x is equated to r. We get these informations from these 3 pivotal and vital points. Now that we have got our informations, we're ready to proceed more further. Before that, we need to understand a basic difference which most of the people misunderstand. Is when I'm saying that the projectile motion only works due to the presence of gravity, and the statement also declares that it is the y which is for which it's working, that the motion is working in favor of y. So doesn't it consider the x to be in the calculation? Actually it doesn't, but does not the acceleration or the velocity at x-axis matters? It doesn't matters that much, but it exists. What I'm trying to tell you is, suppose at some point, suppose at this point, and at this point, and at this point, and at this point, there's a velocity that the object was thrown at a velocity of v naught. So there's a velocity at every point, there is a velocity. At every point there is a velocity. This is the horizontal component of the velocity, this is the vertical component of the velocity, and so on. So the Vx naught here and the Vy naught here, what the statement tells us that the Vy naught is considered in the calculation, but the Vx naught is not that much impactful. Why isn't that much impactful, and why it's considered to be 0? Yes, it is considered to be 0, but why it's considered to be 0? Because when I'm throwing an object, it's going against the gravity. It going at after a certain point of time, it's moving along the gravity. So the Vy naught, the rate of change of displacement is logical, but when it's moving along the trajectory, the Vx naught always stays the same. So it stays at it's equated to a constant value which never changes. So it's Vx naught, this is Vx naught, this is Vx naught, and every Vx naught here at every point is a constant value. Suppose it could be 3 meter per second, so at every point it's 3 meter per second. If it's 5 meter per second, at every point it's 5. So it doesn't changes. So when we differentiate this okay, when we differentiate this velocity in the respect of time, we get ax not equals 0. So that's why we don't consider Vx not to be some value, it's considered to be null. That's why the Vx not is considered to be null and the Vy not is not. Then if the V naught, if the V naught is Vx naught square, the Vy naught square, then if the Vx naught turns out to be 0, then this what remains is Vy naught square and it's equated to Vy naught. So the Vy is directly equated to Vy naught. So now let us move further and solve some questions via which we will be figuring out some equations. We will be deriving some equations as we go through these questions. The first question of mine is what the T1 is equated to. The second is what T2 is equated to. The third is what is T is equated to. The fourth is what maximum height is equated to. Fifth is what the horizontal bar, the horizontal range is equated to. And the sixth is what the R maximum is equated to. So let us start with the first. Before starting answering those questions, I really want to explain some, not some, as one and very important concept, which is the concept of initial final. The initial final concept at a linear point is if we draw a line, then the initial point, if we consider this to be initial point, then automatically the another point of this line will be considered as the final point. In the projectile motion, the curve motion, if this point is considered as an initial point, the point opposite to the initial point is final point. This all obviously this becomes the final point, right? So this concept is going to be applied when I'm going to solve these questions. First answer. If we draw the diagram helps us a lot. Here we go. Okay. If we draw a diagram right over here, and this is V1, okay, this is initial and this is our final point. This is final point and this is initial point. At maximum point, this is the final point. At the time flight, what we had seen before was we got the time flight at the maximum point. We got our time flight at the the time of rising, the T1. We got our time of rising at the maximum point. So the maximum point will be considered as a final point while calculating the time of rising. So this is final and this is initial. We know that V is equals U plus AT. Now, as we mentioned before, that this motion calculates and it takes in the Y. Actually, it considers the Y to be the major part of this, and this works at the Y. So this A will be turned out as G, and in the first phase while getting T1, this was working against the gravity, that's why it's minus G. This is T1, this is V naught. Before we mentioned that the V naught, due to the Vx naught being 0, the V naught was directly equated to Vy naught. So this V naught or the Vy naught, whatever you say, this would be considered as Vy naught. You can write it as Vy naught and minus GT1, and the velocity, this is the final velocity. This is Vy at the maximum point. This is Vy. Earlier we had seen that the Vy was equated to 0 at maximum point, and then the Vy naught is Vy sine theta naught minus GT1. So the Vy sine theta naught is equals GT1. Oh, sorry, it's V naught. V naught sine theta naught minus GT1. V naught sine theta naught equals GT1. So the T1 turns out to be V naught sine theta naught divided by G. This is the equation. This is the formula. T1 equals V naught sine theta naught G. So we got our first answer, that V naught, T1 is V naught sine theta naught divided by G. Now for the second question, what it asks us to find the T2, what the T2 is equated to. See, if the object in a projectile motion is thrown along the angle theta naught at initial, when it will be going down or it will be dropping, the theta naught, the angle will of the final will be equated to the angle when it was at the initial. So the initial angle is equated to the final angle. The angle of throwing is equated, is the same of when the angle of falling is created. So the angle of falling and the initial angle are same. So the T1 is also equals T2. So we got our second answer is that the V naught sine theta naught divided by G. Now what is time flight? The time flight is the sum of these two. So it will be turned out as 2 V naught sine theta naught divided by G. Right? Now we are left with these three questions. Maximum height, horizontal range, maximum horizontal range. Maximum height. So this, at this point, is the maximum point, and this height is considered as the maximum height of a projectile motion. So this is the final point here, and if this is the initial point here, then we know that v square equals u square minus 2gh. Why we written this equation? Because it has the h, the height here. That is why the equation we written before, the v is equal to u plus at, it had any, it had no height variable here, but in this formula it has the height. This v is the final, at the final position. This v is the v velocity at the final position, so it turns out to be 0. This u is v naught square minus 2gh, 2g maximum height, right? Now if we write that v naught square is equated to h is equated to v naught square divided by 2g. If we break it down, this v naught square, then it can be written as v naught square sine square theta naught divided by 2g. So the maximum height is equals v naught square sine square theta naught divided by 2g. Now we got this question also, that the maximum height is equals v naught square sine square theta naught divided by 2g. Then we need this r and this r max. Horizontal range. What is the horizontal range in projectile motion? The distance covered at x while traveling the in the curved trajectory. The travel distance at x is your horizontal range. So that is what the horizontal range means actually. So how we'll be able to get this? We know that x is equals vt if the acceleration is 0 at x. At x the acceleration is 0 as we had seen before. So x is equals vt. This t here, the initial position is this and the final position is this, right? This is the initial and this is the final. So this t turns out to be the time flight, and this v turns out to be the initial velocity, and this x is the horizontal range. So r is equals to v naught t. Okay. Now this t, as we had derived the formula of t was equated to 2 v naught sine theta naught divided by g. We can put this right over here, the 2 v naught sine theta naught divided by g, and this v naught remains the v naught. So 2 v naught square sine theta naught divided by g can be written as this. But here earlier we had seen that the v naught is equated to v y naught, which is v naught sine theta naught. We had seen that. But for this, we'll not consider this. This is wrong for this because we are calculating a horizontal term, right? At horizontal we are calculating, so we are calculating, we had our acceleration at horizontal was 0, so we need our velocity at horizontal, which is constant and which is not 0. That this is the very first time I'm not telling you that the velocity at horizontal is considered to be 0. It's not considered to be 0 here, so we can write that v naught cosine theta naught multiplies 2 v naught sine theta naught divided by g. Now this sine theta naught and this cosine theta naught, with this cosine theta naught, this 2 and this sine theta naught, we know that sine 2 theta is equals to sine theta cosine theta. So taking these three, we can turn it out as sine 2 theta naught, and then what remains is v naught square, and this, the g remains the g. So this is the formula, v naught square sine 2 theta naught divided by g. So we got our horizontal range. Now we want to get our maximum horizontal range. So I have to have the difference between the horizontal range and the maximum horizontal range. The horizontal range and the maximum horizontal range both are not that much different. It's almost similar. See, the horizontal range is what an object can travel in total, what distance it can cover total at x. But the maximum horizontal range tells us that what distance you can cover maximum if I throw you along some conditions. The condition, let's assume that there is a condition that the theta has to be equals 45 degrees. So the horizontal range then changes, and if I write that the theta is 35, so it's less than 45, it won't work. Why? We'll be seeing that. But it's a condition that the theta naught, if the theta naught gets equal 45, and if it tries to get a bit lesser than that, so the trajectory won't change for it, right? So it's the maximum, the trajectory won't collapse at x anymore, so it's the maximum that it can collapse at x. So for the theta, it collapsed the maximum, and when it collapsed the maximum at x, we call it the maximum horizontal range. So it is the maximum distance covered at x by a projectile motion. So as we had seen that the r is equated to v naught square sine 2 theta naught divided by g. For the maximum condition, the trigonometric function related to this um, equation or formula, the value of that trigonometric function gets equated to the maximum value. So here the trigonometric function related to the or associated to this formula is sine theta naught. So 2 sine 2 theta naught is equals the maximum value of sine theta naught is 1. So it is the condition for the maximum here. So the sine 2 theta naught, the plus 1 is equals plus 1. So plus 1 can be written as sine 90 and this can be written as sine 2 theta naught. So this is equated to sine 2 theta naught equals 90 and then theta naught is equals 45. So for sine 2 theta naught, for the maximum value of sine 2 theta naught, the theta naught turns out to be 45 and it's the maximum angle also for which the distance at horizontal will also be the maximum what it will cover actually. So if we put this value right over here, then v naught square sine 2 multiplies 45 divided by g, so it turns out to be 90, and sine 90, as we had seen that sine 90 is 1, so v naught square divided by g is equals r. So this is the formula for r max. So we also got our last question, v naught square divided by g. Now there's an important basic of displacement. What we actually understand as just okay, let me just draw a line. Suppose a man started traveling from this initial point. He went 45 meters and then turned back 10 meters. So how much distance he technically covered actually? The resultant, what is the resultant of the distance? So that is called the displacement. The displacement is the overall distance it's covered, or the resultant of the display of the distances. The distance it covered was 45 plus 10 is equals 55 meters, but the displacement was 45 minus 10 equals 10 meter due to he came back 10 meters. He came back 10 meters at opposite, so he stood here finally, and for here the displacement is 35 meters, so it's equals 35 meter, right? So this is the displacement. Now for projectile motion, if there is an object being thrown at a certain height, from a certain height, let's consider it as y. If it's being thrown from a certain height, then we know that the h is equals ut plus half gt square, right? This h is the displacement at for the horizontal vertical axis, let's say. So y minus y naught is ut plus half a t square actually. So this is y naught, this is y naught, this is y naught, and this is y naught, right? The initial y naught had a value of something meter or something centimeter, something feet or whatever, but the final y is 0. So this is 0 minus y naught is equals ut plus half at square, gt square. So the minus y naught is gets equated to ut plus minus y naught equals ut plus half gt square. So this concept will help us solving a lot of problems. Okay, now we'll head up to another important relation. If an object is is thrown at v naught velocity along theta naught angle, and if it's working against gravity, it's going upwards, right? It's going upwards. It's also moving at horizontal so that it creates a projectile motion. It's a curved trajectory. But as we mentioned before that Vx is negligible. We considered it as null. We considered it as constant, and after differentiating it, it becomes null, right? So we'll not consider this Ax, right? So the acceleration, the vector of acceleration is Iax plus Jay, right? So the Ax turns out to be 0. And this object is working against gravity, then minus J vector at perpendicular, and the Ay is equals G. So G. So A vector equals minus JG. This is the vector expression of a projectile motion. If someone asks you about that, draw a diagram following this equation, you must draw this projectile motion. That is the answer actually. That is the answer for this. So this is a very important equation. We'll be needing this equation later on. We are going to derive a very two very no, not two, there are three actually. X, what is y in projectile motion, and what is uh, tangent. The tangent of the angle, or the y with without time. So what is the necessity of this x and y, and with y without time? Why we need these x and y's? Why can't we solve any problem with what we have already? See, if I show you a problem where, suppose an object is being thrown at v naught velocity along theta naught angle at horizontal, and if there is a wall, it's a wall, and the object is thrown, now I want to know what is the height of the wall, right? I know the theta, I know the velocity, I know these parameters, but can I get this y actually? Because in projectile motion we had talked about these 3 points: initial, final, maximum point. We haven't talked about this y at any point or x at any point. Like if I want to figure y in this point, at this point, if I want to get that y, or if I want to get that x at this point, I can't, because we hadn't derived any equation. So we'll be looking after that. So we'll be looking for this y, these the y at any point I want, right? Okay, so for getting the y at any point will be needed to understand the concept of position vector. We know that position vector is ix plus jy if it is two-dimensional. If it's three-dimensional, then ix plus jy plus kz. We know that, right? So the projectile motion is a 2D motion, so this equation will be needed actually. So R naught, the concept of displacement is also applicable for position vectors. See, the displacement, as I mentioned earlier, the displacement is the resultant of distances, right? If a man went 45 meters straight and then came back 10 meters, so the resultant is 35 meters, so that is its displacement, right? So the displacement is the difference in distances, right? It is the difference in distances. it also it also applies for the position vectors, that r, this r can be equated to something x minus x naught. So as we know that x equals v naught t plus half a t square, right? So for the position vector, we'll be writing this, denoting this velocity as a vector quantity half. Acceleration is also turned to be a vector, so this is the position vector. If I take the magnitude out of it, this is x minus x naught, or if I keep it as vector, so v naught t plus half a vector t square, then x is equals x naught plus v naught t plus, okay, plus half of just plus half of a vector t square. So this is the very important thing here. So if we move forward, there's no difference, or no, it is no different in the projectile motion also. We talked about the linear motion, we explained the linear motion, yeah, but it's no different for the projectile motion as well. So in the projectile motion, it can be written as r, position vector is r naught, because r naught v naught t plus half a t square or whatever. So the position vector here can be written as ix plus jy, and the r naught can be written as ix naught plus jy naught, and this is also, these are also vector quantities. So v naught is I vx naught plus j vy naught plus half of a I ax plus j ay t square, right? Now at the initial point, the x is 0 and the y is 0. That means the x naught is 0 and the y naught is also 0. So it vanishes from the equation. So we'll be writing that we will be starting from the I vx naught plus j vy naught plus half I ax plus j ay t square. Now this vx naught and this vy naught can be written as v naught cosine theta naught, and this j v naught sine theta naught plus half of iax plus jay. So half of iax and then half of jay plus t square, sorry, not plus t square, it's t square only, Oh, here is a t square as well. Here's a t square as well. And okay, there's, I think there's a t and there's a t, there's a t as well, there's a t as well. Okay. Now, if I take this I I unit vectors and side them up, so I v cosine theta naught half I a x t square not this is half j vector a y t square. Now, as I mentioned earlier, that v naught at x is constant every time. Differentiating it, it will be turned into a naught equals 0 for x. So the ax here is 0. So I v naught cosine theta naught exists, t exists, but this vanishes. And basically what remains is j v naught sine theta naught t plus half j vector a y t square. Now it is equals to I x plus jy, right? So the coefficients of j are v naught sine theta naught t here, and this j this half and this ay t square, right? So if I equate the coefficients, so that will be v naught cosine theta naught t and y equals v naught sine theta naught t plus half a y t square. Now I mentioned earlier that the ay the acceleration or the ay is minus jg. So if I put it here, that it's minus, if it's minus jg, it's vector actually. So the plus half no, it's not vector, this is okay, done something wrong. This is j a y t square and this ay is minus g, that's why it's j and this is g and there's a minus and this t square and this sine theta naught t and there's v naught and there's y. So this is y equals y is equals v naught sine theta naught t minus half gt square. Let me clarify for you that y equals v naught sine theta naught t minus half j, or sorry, the coefficient of j will be written, so the j will not be here, t square, right? Here the ay will be replaced as minus g, so then here there will be a minus g here, right? And this x is equals v naught cosine theta naught t. Now if the v naught is x, if the x is equals v naught cosine theta naught t, then the t is equals x divided by v naught cosine theta naught. Then if I put it in y, then it will be cosine theta naught minus half g x v naught cosine theta naught whole square. So this will turn out to be x tan theta, due to the v naught is being cancelled, x, and this is sine theta, and this is minus this g x square, and there's 2, and there's v naught square cosine square theta naught. So here you go. So y is equals x tangent theta naught minus gx square to v naught square cosine square theta naught. So if I summarize, and x is equals v naught cosine theta naught t, y is equals v naught sine theta naught t minus half g t square, y without time is v naught sine theta x tan theta minus gx square 2 v naught square cosine square theta naught. There was a t1 formula, v naught sine theta naught divided by g equals t2 as well. The time flight was twice of this t1 or t2, or it's equals to t1 plus t2. Then the height, the maximum height was v naught square sine square theta naught divided by 2g v naught square divided by 2g. The horizontal range was v naught square sine 2 theta naught divided by g, and the r max was v naught square divided by g. So these were the formulas